Okay, so we are live, I guess. Are we? Yeah. So we are live, and in this live video, we are going to solve all the problems of MIT Integration B from 2010, the year when it started. Not it started, but the year when it started to publish problems online, to 2023, to the current year. So it's going to be a lot of fun, and it's going to be a tough task too, since we are solving all the problems. And hope it's an excellent journey with you guys. Yeah. So let us start. Uh, MIT Integration B. Hmm. Let's start with 2010. I guess it's going good. Is it? Okay, yeah, that's going good. And now, okay, that's fine. Now let's begin with this integral. Before we begin, can I just confirm it from my phone if the sound is clear or not? Those things, because if it's not, then it would be a trouble. Before we begin, can I just confirm it from my phone? Oh, okay, it's fine. Yeah. The first is this problem 1. So we have this integral from 0 to pi by 2, and this product of trigonometric ratios. And since it's from 0 to pi by 2, we immediately think of using beta gamma functions and this identity. Integral from 0 to pi by 2 of sine to the power m of x cos to the power n of x dx. The integral for this function is actually 1 by 2 of beta m plus 1 by 2 n plus 1 by 2. So we'll use this identity, and after this we can just use the beta function definition. Beta of xy is equals to gamma x gamma y by gamma x plus y. So this will solve the problem. Let's begin. An integral from 0 to pi by 2 sin x. Again, break sin 2x into 2 sin x cos x, and we can also break sin 3x into 3 sin x minus 4 sin cube x. Yeah. And then here's dx. After this, we will have integral from 0 to pi by 2. We can take 2 out as common, and over here we will have sine cube x cos x minus also there's 3 sine cube x cos x minus 4 sine to the power 4x, sorry, sine to the power 4x. Is it 3 4 5, sorry, sine to the power 5x, and then cos x dx. And now integrating this is easier since we have the integral in this form. So that will be 2 times 3. This is 1 by 2. Beta of 3 plus 1 4 by 2 is 2, and then 1 plus 1 2 by 2 is 1 minus 4 times 1 by 2 of beta 5 plus 1 by 2 6 by 2 is 3, and 1 plus 1 by 2 that's 1. And now 2 3 gamma 2 is 1, gamma 1 is 1 by gamma 3 is sorry for that. Okay, so gamma 2 is 1, gamma 1 is 1, and gamma 3 is 2 minus 4 by 2 times, again this is gamma 3 gamma 1 by gamma 4. So gamma of 3 is 2 factorial, so that's 2. Gamma of 1 is 1 by gamma of 4 is 3 factorial, so that is 6. Now we have 2, 3 by 4 minus this one is 2 1 is 2, 2 2 is 3, 2, so 2 by 3. Yes, I'm doing right. I hope it's right. Okay, so after this we have 3 by 2 minus 4 by 3, so that comes out to be 6. 3 3 is 9 minus 4 times 2 8, 1 over 6, and that's the answer. We can check the answer too. 1 by 6. Let's go to the next integral. Integral from 0 to pi root. It's kind of similar one. Don't really have much difference. Now for this integral, we will use the same idea. We will just break down sine to x and then make it 2 sine x cos x. 8 sine cube x cos cube x cos x dx. Or we can take 8 out of the integral since it's a constant, and then we will have sine cube x cos to the power 4x dx. So we have, this is 1 by 2 beta of 3 plus 1 by 2, that's 4 by 2, that's 2, and 4 plus 1 by 2, that's 5 by 2. Now this is 4 into gamma 2 gamma of 5 by 2 by gamma of 9 by 2. Their sum is 9 by 2. Now we know that gamma of n is just n minus 1 factorial. Yeah, so gamma of n will be n minus 1 times gamma of n minus 1. Can use this property. 4 into gamma of 2 is just 1, and gamma of 5 by 2, let it be as it is, cause in the denominator this is gamma of 9 by 2 will be 7 by 2 into 5 by 2 into gamma 5 by 2, and we can make the cancellation. Then we will have 4 times 2 8 times 2 16 by 35, and that's the answer. 16 by 35 is the answer. Let's go to the next integral. Okay. Yeah. Before I continue, let me just make one more confirmation that it's going well. Before I continue, let me just. Okay, it's going well. Okay. Now for this one. For this integral, I think basically we can just assume this part as y and then make it in other part, or basically we can also assume this part as y since it has some odd random powers. Okay, so that will help. Now if we just let y equals to x minus 1, we will have y plus 1 equals to x. After that we can just substitute the values of y for x, and that is x is y plus 1 square, and over here it's y to the power 1 by 3, and for this dy equals to dx. You can clearly see that, so dx equals to dy. Yeah. And after this we have y plus 2 whole square, y to the power 1 by 3 dy, and that's y square plus 4y plus 4 and y to the power 1 by 3 dy. After this you can just distribute and then find the integral. So this is 2 to the power y to the power 7 by 3, 4 times y to the power 4 by 3 plus 4 times y to the power 1 by 3 dy. Now we can do integration. That's y to the power 10 by 3 by 10 by 3 plus 4 times y to the power 7 by 3 by 7 by 3 plus 4 times y to the power 4 by 3 by 4 by 3 plus c. 4 gets cancelled out and nothing. We don't need to do anything else for the others. You can keep as it is. And yeah, I think this is the solution, except that now we need to substitute y as x minus 1. So we can also take y to the power 4 by 3 common. Yeah. Also 3 as common. So if we take 3y to the power 4 by 3 common, we get y square by 10 plus 4y. Is it y? Yeah, 4y by 7. Is it? Yeah. And then plus 1 plus c, and then now y is just x minus 1. So 3 x minus 1 to the power 4 by 3 x minus 1 whole square by 10 plus 4 times x minus 1 by 7 plus 1 plus c. So this is the solution. Let me check it. 3x minus 1 to the power 4 by 3 and then x minus 1 whole square by 10 and 4 by 7. Yeah, 4 by 7. Yeah, that's it. Let's go to the next one. This integral. Okay. Now for this integral, I think basically we can just assume this. You can use substitution, or we can also do integration by parts. Yeah. Because this gives us minus 1 by x square, and we'll also get x square by 2. So the cancellation occurs, and that's helpful. Okay, so let's do. So if we do integration by parts with this as u and this as v, we get log of 1 plus 1 by x times x square by 2 minus integral of, now differentiate this, we get 1 by 1 plus 1 by x, and then we will have minus 1 by x square. If we use chain rule, we have differentiate the inside, and also we get here x square by 2. So that's how it's helpful doing integration by parts. And again, now cancel this out. Yeah. And then we have log of 1 plus 1 by x, we have x square by 2 minus, and minus become plus, you can take 1 by 2 out, and then we have x by x plus 1. And of course now it's really easy to integrate this part. We can just add plus 1 and minus 1. Yeah, we can just add plus 1 and minus 1. And then we have log of 1 plus 1 by x, x square by 2 plus 1 by 2. So we will have 1 minus 1 by x plus 1. So when it's 1, it will be just x, and when it's 1 by x plus 1, it's just ln of x plus 1. So this integral is solved, and I hope the answer is correct. X square by 2 ln 1 plus 1 by x plus x by 2 minus ln x plus 1 by 2. Yeah, that's correct. Yeah, let's go to the next one. Sorry. Okay, so for this integral, first of all, we would not want to have log x inside the sign function, so we will just assume y as log x, and while doing so, the 0 will convert to minus infinity. Yeah, since log of 0 is minus infinity, but we would rather want plus infinity than minus infinity. So basically we also add a negative sign over here in the substitution, so that we will have a plus infinity. Okay, so we can do that, or even if we do not do, that doesn't really matter. Let's leave it as it is for now, and then we will have dy equals to 1 by x dx, and then we will have integral from minus infinity to 0, log of 1 is 0, log of just minus infinity, and we will have sine square y, and but we cannot now we cannot really have this in place of dx. We cannot really write x dy in place of dx, because we are going into the world of y, and still having x dy per dx doesn't really help us. So we will make conversion over here. We'll use the fact that this can be changed into e to the power y equals to x, and then we will use e to the power y dy equals to dx. So this is helpful for us, and dx equals to e to the power y dy. Now after this, basically we can just change sine square y into cos, so that it's easier to deal with just first power rather than second power. So we can do that change. Also we can make y as minus y. If we make y as minus y, so basically we will have sine of minus y, and then sine square, yeah. So this will be minus sine y, minus sine y. So there will be product of 2 minus sine y, and again minus cancels out, so that's just sine square y. Yeah. Now I'm going to replace. Okay, so this doesn't get erased. Now I'm going to replace y by minus y, and that changes it from infinity to 0, and sine square minus y will just be sine square y as I saw it right now, and e to the power minus y, and this will be minus dy. And so this minus will change the orders of limit. Basically, if we have a to b f of x dx, and if we extract a minus sign from this, we will have integral from b to a. So we will use this property now. Yeah, and if we use this property, we can change this from 0 to infinity, sine square y e to the power minus y dy, and then we will change sine square y into 1 minus cos 2y by 2. So that is 1 minus cos 2y by 2 e to the power minus y dy. Now we can take 1 by 2 out, and we have 0 to infinity e to the power minus y minus integral from 0 to infinity e to the power minus y cos 2y dy. Okay, so now to deal with this integral, it's not that hard, but on the other one we will need a standard formula, e to the power minus y by minus 1 from 0 to infinity. So at infinity we have e to the power minus infinity, so that's 1 by e to the power infinity, and 1 by infinity is just infinity, so that's 0. Okay. So this will be 0 at infinity, and minus at 0, and this is 1 and minus 1, so we have 1 by minus 1. So you see, that's just 1. This minus gets plus. So this one is just 1, and minus. For the other one, we will need a standard formula, which is like this. The formula is integral of e to the power ax cos bx. This is the IC formula, and I think you know it. Is e to the power ax by a square plus b square a cos bx plus b sine bx. So we need to know this formula, and with that it gets a lot easier. So 1 by 2, we will have 1 minus, this will be e to the power ax by minus 1 square is just 1 and 2 square is just 4, and a cos bx plus b sine bx. So this is the integral, yeah, and it's going from 0 to infinity. Okay, so that is it, and we have 1 by 2, 1 minus, now if we evaluate this at infinity, of course e to the power minus y will dominate, because denominator it will get extremely large since it's increasing exponentially. So any function such as trigonometric, not all actually, such as trigonometric or polynomial, if there are any function f of x, and in denominator if we have e to the power x, and this for this, if x is going to infinity, of course e to the power x will increase much faster than trigonometric or polynomial. Basically for cos and sine that was true, for others I haven't checked though, since because at infinity also the cos and sine values will lie between -1 and 1, you know? So that's why it grows too fast that it will of course go to 0, so we will use that. So at infinity it's 0 minus, at 0 we need to do it, this will be 1 by 5, and this is -1, and this is 0. Okay, and then we have 1 by 2, 1 minus, this will be -1 by 5, but that's again +1 by 5, so it's 1 by 5, so it's 1 by 2 into 4 by 5, that's just 2 by 5. And I think that's the answer. I hope you understood this. Yeah, it's just this formula and nothing else, and some application of limits as well for evaluating it infinity and 0. Yeah, I hope you understood this. Let's check the answer. It's 2 by 5. Let's go to next one. Okay. So now this problem. So this problem is not that hard, but we need to have some tricks or ideas, sort of things, that we have to add whatever is there in denominator, 3 to the power 3 times e to the power x minus 3 times e to the power x by 1 plus 3 times e to the power x dx. Now when it's this, we just have 1 minus 3 times e to the power x by 1 plus 3 times e to the power x dx. Now the benefit of this manipulation is, now if we let y as 1 plus 3 times e to the power x, we will have dy equals to 3 times e to the power x itself dx. So this will be just dy when this is y, and that means we can have ln y. So this is x minus ln of 1 plus 3 times e to the power x plus c. So you see, this manipulation really made our problem a lot easier. And I guess that's the answer, x minus ln of, okay, so here's a different form. So basically what we can do is we can let this as ln of e to the power x minus ln of 1 plus 3 times e to the power x. We can do this, and after that we know that ln of a minus ln of a minus ln of b is just ln of a by b. We'll use that, so that this is ln of e to the power x by 1 plus 3 times e to the power x. So this will be ln of 1 by e to the power minus x plus 3. And now minus ln, so ln of 1 by a is just minus ln a, you know? Minus ln a. So this is minus ln of e to the power minus x plus 3. And this is the answer. Now the one that's given. Yeah, this is the answer. Let's go next one. For this problem, basically we change into tan and sec. Okay, so for this problem, we can basically change this in tan and sec, so that when we let y as tan, we get dy as sec square x dx, and that really helps. Okay, but how do we do that? Let's see. First of all, we can have sec x to the power 5 dx, yeah. But again, to convert this sin x cube to tan, we need to divide by cos cube x or multiply by sec cube x, so that we will have tan cube x by sec cube x dx. Yeah. So this is how we change, and now we have integral from pi by 4 to pi by 3 sec to the power 8x tan cube x dx. Now we know that sec square theta minus equals to 1 plus tan square theta. We'll use that. Now we also let y tan square, it's not theta, theta. So now we let y as tan x, and so we get tan pi by 4 is just 1 and tan 60 is √3. Okay, and then we can have sec to the power, we can change that to sec to the power 6x and sec square x dx, so that we can keep sec square x dx as dy, and we can change this to cube of sec square x. And now sec square x is just 1 plus tan square x and its cube, and tan square x is just y, so 1 plus y square cubed. So we can make that change over here. So we can have 1 plus y square cube times sec square x dx will be just dy and divided by y cube. Now you see, it's really easier. Now it will not be a lot tough to deal with this, since this is just a cube plus 3a square b plus 3ab square plus b cube by y cube. Yeah, dy. I think now you can evaluate this integral part by part. Yeah, now I don't think it will be a lot harder, since these are just normal polynomial things that we do. Now I leave it on you. Just evaluate these terms part by part and then substitute the limits to get the answer. That's not that hard, so I will leave it for you. And if you do that, you will get the following answer: 16 by 3 plus 3 by 2 ln of 3. Okay. Now let's go to the next question. Yeah. Now for this problem, we can basically let the other thing. Okay, that's fine. For this problem, we can basically let the y equals to root under x to the power minus 1. And the reason I'm doing this is, if we let root under x to the power minus 1 as y, in dy we will get 1 by 2 root x to the power minus 1, yeah. And this is what we already have here. So there's dx and there's 3x cube. Of course there's these things as well, but this one is already here. So dx by root x to the power minus 1 can be used as a substitution to go to dy. So now we will have 2 dy by 3x cube. Yeah, sorry, not 3x cube, it's actually 4x cube. 4x cube. So we will have this, and you see that this expression that we already have here can be used to not dy, that's dx. So this can be used to go to the dy world, and also x cube and x will multiply to get x to the power 4, and again x to the power 4 can be changed to y as y square plus 1. So that helps really. So yeah, you will see. Okay, we will have dy equals to 1 by root 2 root x to the power 4 minus 1 times 4x cube dx. Yeah, and after this we have 2 dy by 4x cube dx equal, not dx, 4x cube equals to dx by root under x to the power 4 minus 1. Yeah, now this will cancel it to the group 2. Now we can use this as substitution to get into this. Yeah, and when it's 1 it's 0, when it's infinity, and that will be 1 by x will be as it is, and dx by root x to the power minus 1 will be dy by 2x cube. And now we have 1 by 2 integral from 0 to infinity dy by x to the power 4. X to the power 4 is just y square plus 1. Yeah, y square equals to x to the power 4 minus 1 is given. So y square plus 1 is equals to x to the power 4. And that is 1 by 2 integral from 0 to infinity dy by y square plus 1. So that's 1 by 2 tan inverse y, and it's going from 0 to infinity. Yeah, it's going from 0 to infinity. So this is just 1 by 2 tan inverse infinity is pi by 2 minus tan inverse 0 is just 0. So the answer is pi by 4. Pi by 4. Yeah. The previous answer was 16 by 2 third log 3. Yeah, it was. Okay, let's go to the next one. Now for this problem. Now this problem involves a little of clever substitution and clever tricks, basically we would have to find a way that if we take x to the power 5 outside from this expression, if we take out this as common, we will have over here 1 by x to the power 5, and here we will have x to the power 6 but in denominator. So that will act as substitution. Okay, so let me do it and you will know. Okay, so it's dx by x to the power 6 1 plus 1 by x to the power 5. Now if I let y as 1 plus 1 by x to the power 5, dy will be minus 1 by x to the power 6, which is what we have here exactly. Yeah, we have this over here. So this is minus dy equals to 1 by x to the power 6 dx. And that's really helpful now. Minus dy by, this is just y, and you see we have solved the problem. This is just ln of y plus c, and y is minus ln of 1 plus 1 by x to the power 5 plus c. And now to remove the minus sign, we can do something like this. We can first just take the LCM, x to the power 5 plus 1 by x to the power 5, and now we can just inverse this thing, and ln of x to the power 5 by x to the power 5 plus 1 plus c. Yeah, okay. and wait. So this, while doing this thing, is it just uh, I also will have, sorry, I made a mistake over here. So while differentiating, uh, we had y equals to 1 plus x to the power minus 5, yeah, minus 5. So dy will be 0, and then over here we'll have minus 5 x to the power minus 6, yeah. That was a mistake, so it should have been minus 5 over here, and we will also have by 5 over here, and by 5 over here, by 5 over here, and the minus 1 by 5, minus 1 by 5, and then 1 by 5. So now that's the answer. 1 by 5 ln of x to the power 5 by 5 plus 1. Okay, let's go to the next one. Okay, for this problem, we can just let y as root 10x. But why that? Okay, but why do we let that one? Okay, so let's see. If we just let y as root 10x, we will have dy as 1 by 2 root 10x, yeah, and then dx. Okay, so now what do we have from this? We have that dy equals to 1 by 2y, and then if we do it 2y square, we'll also have to put here root 10x dx, yeah. And then, yeah, since this is just y, if you have to put here 2y square, we will have a root 10x dx. So, and wait, this is not all. We will also have something else over here as well. We will have 1 by, is it 1 by, not 1 by, we will have sec square x dx. Okay, and now this sec square x will be sec square theta equals to 1 plus tan square x, 1 plus tan square x dx. Okay, and so this can be also written in terms of y. We will have dy equals to 1 by 2y square root 10x, and then this will be 1 plus y to the power 4 dx. And now we'll have 2y square by 1 plus y to the power 4 dy equals to root 10x dx. So basically all of them could be changed to tan due to this substitution didn't really matter, but this helped, in fact. This in fact helped us to solve the problem. We haven't really solved it yet, but I think it gets us closer to solution. So now let me just rewrite this problem in terms of y. So tan of 0 is 0, tan pi of y is 1, and root is also 1, and root 10x dx is now 2y square by 1 plus y to the power 4 dy. And after this, how do we deal with this one? It probably seems like now we can use beta gamma functions, or can we? It seems like we can use beta gamma functions to me, but I'm not really sure about that as well. I think we have to go with some other techniques, not really beta gamma function, since beta gamma function involves 0 to infinity, but we don't have that. Now let's undo that. Integral from 0 to 1, 2y square by 1 plus y to the power 4 dy. Like what we can basically do is We can make this as y square plus 1 plus y square minus 1 by, and over here we have 1 plus y to the power 4. 1 plus y to the power 4 dy. This is one of the standard techniques though. This is one of the standard technique. And now we can just separate these into two integrals. 0 to 1 y square plus 1 by 1 plus y to the power 4 plus y square minus 1 by 1 plus y to the power 4 dy. Now let's deal with these integrals individually. Okay. Okay. So we have a space over here, so I will use this space. The integral from 0 to 1 y square plus 1 by 1 plus y to the power 4. For this integral, we can basically do something like this. 0 to 1, we can just divide numerator by 1 by y square. That gives us 1 by y square plus y square dy. Yeah. And now we can notice that we can just complete the square in the denominator. And if you complete the square, we will have y square plus, but we don't want plus over here. But I will tell you the reason why we don't want plus over here. We'll just make it minus 2y 1 by y plus 1 by y square plus 2. Yeah, you also know the reason why I didn't complete it from a plus b whole square and not y from a minus b whole square. So 1 plus y by y square, and then 1 minus 1 by y whole square plus 2 dy. Now you see, if we let this as g or something, any variable, let's say a, then this will be dA. Yeah, 1 and then plus 1 by y square. So if we had plus over here, it would be minus. It would have been minus in the denominator, in numerator. So that's why I made it minus over here. Now we can let this as g as 1 minus 1 by y. So at 0, this will be minus infinity. At 1, this will be 0. And this will be just dg by g square plus 2. So that's 1 by root 2 tan inverse g by root 2 from minus infinity to 0. Yeah, and that will be 1 by root 2 tan of 0, tan inverse 0 is 0 minus tan inverse minus infinity is minus pi by 2. Yeah, so this is actually pi by 2 root 2. Okay, now other one is also similar, except that we will have over here minus and we will have a plus over here. Yeah. Yeah, okay, so let me just do it short. For this integral, we will have integral from 0 to 1. We will have 1 minus 1 by y square by, we will have y plus 1 by y whole square and then minus 2 dy. Now we'll let this as g. So we will have integral from this is infinity, this will be 2. This will be 2. Yeah. Okay, yeah, this will be 2. And we will have dg by g square minus 2. And then that will be 1 by 2a ln of g plus 2 by g minus 2. This is also a standard formula from infinity to 2. Okay, and then we can just evaluate these at 2 and infinity. 1 by 2 root 2 at 2. This will be ln 4 by 0. Yeah, but ln 0 is again infinity, so that doesn't really make sense though. Or okay, I have made a mistake. This is g, and I have also wrote wrong formula. It's not So I'm really sorry for all the mistake that I've been doing. It's actually minus 2 in the numerator, not in the denominator. So z minus 2 by z plus 2 from infinity to 2. Okay, so this is correct formula, and I'm really sorry for messing it up. Okay, and now when we have 1 by 2 root 2, this is ln of, and this is root 2, not 2, right? Since we have to take square root of 2 over here, so this is root 2. So ln of 2 minus root 2 by 2 plus root 2 and minus, at infinity these two are equal. I don't know what happened. That was some sort of magic. Okay, so this is ln of 2 minus root 2 by 2 plus root 2 and infinity, this is just 1, since these two are equal, so ln of 1 is 0, minus 0. And yeah, I think this is the answer. What's the problem? Okay, I think you got the answer already. So I wouldn't try to write this again in the same slide, since it's going to again just crack. And I think that's the answer. Pi by 2 root 2 plus 1 by 2 root 2 ln of 2 minus root 2 by 2 plus root 2. I guess that's the answer. Let's check. Yeah. And yeah, you can simplify that ln of 2 minus root 2 by 2 plus root 2 to get this expression. Yeah, it works. It works. I can see it in my copy. Let's go to the next one, the next page, or else it's again going to crack. And the next problem is this. Okay, so for this problem, okay, so I think this is one of the famous problem. Yeah, this was also there in Putnam problem. This was also there in Putnam competition, and it's really a famous problem because it involves King's rule. Yeah, I will tell you about King's rule soon. Don't worry. So first of all, we can make a substitution that x equals to tan theta. Yeah, and then we will have tan inverse x equals to theta, and that implies d theta equals to 1 by 1 plus x square dx. Okay, and since theta equals to tan inverse x, we will have tan inverse 0 as 0, tan inverse 1 as pi by 4, and we will have ln of 1 plus tan x, and then we will have 1 plus tan theta, not tan x, plus tan theta, and then we have d theta. Okay, now the idea involved in this integral, in solving this integral, is we will use an identity that says integral from a to b of f of x dx is equals to integral from a to b of f of a plus b minus x dx. This is also known as King's rule, and if you want to see why this holds true, you can just take antiderivative, which is capital F of x. It goes from a to b, and capital F of b minus capital F of a is the integral. Yeah. Now from this side too, we will have capital F of a plus b minus x, and divided by minus 1 because it's the coefficient of x from a to b. Now at b, this is minus f of a. At a, this is plus f of b, and you see that's the same result. That's why it works. We can use that over here, and that gives us I equals to integral from 0 to pi by 4 ln of 1 plus tan pi by 4 minus x, tan pi by 4 plus 0 minus theta, plus 0 minus theta. So this is the application of King's rule. And we have I equals to integral from 0 to pi by 4. Sorry, why is this crashing so much? It didn't really used to start normally. I think I have to delete this. Wait a second. I think it's already there in cache memory, so that's why it's lagging, probably. That's the reason. no, I think it won't do it now. Yeah, and yeah, x plus b. Now we know that I cos integral from 0 to pi by 4 and ln of 1 plus tan of pi by 4 minus theta and d theta. Now we can just use the property of tan a minus b to expand that. So we will have ln of 1 plus tan a minus tan b by 1 plus tan a tan b and d theta. And now if you take LCM, we will have 0 to pi by 4 ln of 2 by 1 plus tan theta d theta. So we will have I 0 to pi by 4 ln of 2 by 1 plus tan theta d theta. And now we can just break this into two logarithms, ln 2 minus integral from 0 to pi by 4 ln of 1 plus tan theta. And now we know that this was our original integral I. This was our original integral I. Okay? So we have I equals to ln 2 times theta going from 0 to pi by 4 minus I again. Yeah. And so we have 2I equals to ln 2 pi by 4 minus 0. So 2I equals to pi by 4 ln 2, and that's why I equals to pi by 8 ln 2. So that's the answer. And let me check if it's pi by 8 ln 2 or not. Pi by ln 2. Let me just check if there have been anyone who joined. Yeah, oh, 3 viewers. So 3 people were there. Yeah, so that's really good to know. Let's proceed. Can I check the chat as well? If there's anything on the chat, anything that people might be. Oh, okay, so there's nothing on the chat. Okay, doesn't really matter though. Now let's go to the other problem. This one. Let me just delete this one. Okay, so for this problem, yeah, okay. So the idea we use for this problem is basically we have x to the power half and x to the power 1/3 as well. So if we let x to the power 1 by 6 as y, then this will be just y cube and this will be just y square. So there will not be any variable with fractional powers or so on. So that's why I made this decision while solving the problem initially in my copy. So we have y equals to x to the power 1 by 6. And also you can see that 64 is just 2 to the power 6. And 79 is just 3 to the power 6. Yeah, so that's why also you can think of this decision. And now if we do that, we will have so y to the power 6 equals to x, and 6y to the power 5 equals to dx. Yeah, so and then we will have integral from 2 to 3. This will be y cube, and then y cube minus y square, and dx will be 6 times y to the power 5 dy. Now after this, we can take 6 out from 2 to 3. We will have y to the power 8, but we can just cancel y square. We do have y to the power 6 by y minus 1 dy. I think after this we will let y minus 1 as z, yeah, we do that. Now after this we can have z equals to y minus 1, and then we will have dz equals to dy. That's how we have 6 integral from 2 to 3. Now this will be z plus 1 to the power 6 by z dy, and also the limits will change. The limits will change from 1 to 2. Yeah, and now we can just expand the numerator. Is g to the power 6 plus 61 g to the power 5 plus 62 g to the power 4, and so on till g to the power still 1 by z dz. Now you can just integrate part by part, and then substitute the limits of integration, and I think that's really easy. That doesn't really require any extra ideas but some calculations only. So now we can just make it part by part integration and then integrate. So I think I should leave that for you, and that gives us 6 times over here. We will have ln2 plus 107. What is that? I haven't made a lot of things, but no, I haven't really written a lot of things though. So yeah, okay, so we have 6 times ln2 plus 10747 by 60. So we'll get this. And yeah, I think that's the answer. 6 ln2 plus 10747 by 10. Is that? 6 ln2 plus 107. Yeah, that's the answer. Okay, so now we have 2 concurrent viewers. So okay, so that's a good thing to know. Can we be on chat if you are using this or not? Can you write in chat if it's if you are using this or not? That will help me. Okay, so let's go to next problem. Next problem from MIT integration B. This one. Okay, so this is our next problem from MIT integration B, question number 13. Now this problem is not that hard, since we know this is a standard derivative of x to the power x. So if we try to differentiate x to the power x, we'll get this, and this is well known, I think. So first of all, we can just take log on both sides. So we will have ln y equals to x ln x. And then we can just differentiate 1 by y times y dash equals to x 1 by x plus 1 times ln x. This is product rule. And then we will have y dash equals to y times 1 plus ln x, and y dash equals to y is just x to the power x times 1 plus ln x. So you see, this is just dy, and right here dx as well. Okay. So you see, this is just dy or y dash, so that's just y plus c, and y is just x to the power x plus c, and that's the solution. Let me just check if there are any. Keep doing the hard work and succeed one day. Thanks so much. Okay, now the next question. This one. Did it. Now for this one, I think we can take out this actually half by 2 common, and then deal with it. Okay, first of all, let us let y equals to s to the power 5 by 2, and then this will be for 0 it's 0, for 1 it's 1, and we will have x to the power 13 by 2 root under 1 plus y, and then dx will be we will have dy equals to half by 2 x to the power 3 by 2 dx. So t dy by 5 equals to x to the power 3 by 2 dx. Okay, so this one is 2 dy by 5. Yeah, and then also x to the power 3 by 2. You see, so 2 dy by 5 times x to the power 3 by 2 over just our dx. And next we have integral from 0 to 1, and we can take 2 by 5 out, and this will be just x to the power 10 by 2. Yeah, and that's x to the power, is it 10 by 2? How come it be 10 by 2? So 5 by 2 was there, and dy equals to 5 by 2 x to the power 3 by 2, and then 2 dy by 5 x to the power 3 by 2 dx, and 2 dy by 5 x to the power 3. Now after that, this comes out to be x to the power 10 by 2, that's x to the power 5, and root under 1 plus y dy. So we have this expression. Yeah, but I think it's going good, but why do I have some other ideas? Okay, I got it. Now we will try to write that x to the power 5 in terms of y. So that gives us 2 by 5 integral from 0 to 1. This will be just y square. Yeah, since y equals x to the power by 2, we will have y square equals to x to the power 5 root under 1 plus y dy. And now we will use the same similar technique as we used previously. We will have z equals to 1 plus y, and then y equals to z minus 1. We will use this technique, and then 2 by 5 integral from 0 to 1. Y is just g minus 1 square root under g dg. And then, sorry for the noise though. Okay, now I guess there won't be this noise. Now after this we will have 2 by 5. Oh, okay, and I don't think I changed the limits. So when we did this, it will be 0 to 1, and when we have z equals 1 plus 5, this will be from 1 to 2. Yeah, 1 to 2. Okay. Since z equals 1 plus 5. Now from 1 to 2, and this will be g square minus 2z plus 1. So this is z square minus 2z plus 1, and g to the power 1 by 2 dg. After this, we will have 2 by 5 until from 1 to 2, z to the power 5 by 2 minus 2 z to the power 3 by 2 plus z to the power 1 by 2 dg. Now we can just integrate it by part, so I don't think that's really hard. And if we do that, and if we just integrate by part by part and then substitute the limits, you will get 4 by 105 times 11 root 2 minus 4, and multiplying this we will have 8 by 5 to 5 11 root 2 minus 4, and that's the answer. 8 by 5 to 5 11 root 2 minus 4. Where is it? 8 by 5 to 5 11 root 2 minus 4. What is the question number? Let me check. 14. Yeah, and basically, yeah. Okay, so I also checked. Let us check this problem in all prime alpha. I think I have checked it there, and I think this was wrong question. Yeah, this answer was itself wrong here. I thought that when I solved it, but yeah, there was still check it. So integral from 0 to 1 x to the power 13 by 2 and square root of 1 plus x to the power 5 by 2. And this is 1. And then dx. Let us check what's the answer. Yeah, I think, yeah, you see, the answer is 8 by 5 to 5, 11 root 2 minus 4. Yeah, so this answer, 7 by 30 is actually wrong over here. And yeah, this is the correct answer. So next problem. Next problem is integral from 1 to infinity, 1 by root under x power, yeah, minus 1. Okay, so for this problem, you can basically let y equals to x square first. Yeah, and then we get integral from 1 to infinity dx by y plus 1 square, and then we had y to the power 1 by 2 equals to x. Yeah, so that gives us dx equals to 1 by 2 y to the power minus 1 by 2 dy. That gives us 2 dx equals to y to the power minus 1 by 2. Okay, did I miss anything? I don't think I really need to change it to other side. I think this is fine. Okay, and let me replace dx with this thing, 1 by 2 y to the power minus 1 by 2 dy. So that's just 1 by 2 integral from 1 to infinity y to the power minus 1 by 2 by y plus 1 square dy. Now the next step we can probably take is to use I don't think we can really use the beta gamma functions. I think my first approach was to use beta gamma functions, so that's why I took it to this form. And next, I probably thought of if this was from 0 to infinity, I would have used the form of beta gamma function of the integral from 0 to infinity of x to the power m minus 1 by 1 plus x to the power m plus 1. I probably thought of using this, and because this is just beta of mn, but here it isn't from 0 to infinity, so this doesn't really work, and there's another way, there's another method for doing this. So that's why I just prepared this before, and in case because we have to try it multiple times, and not all processes are bound to work. Yeah. Okay, so let me make another try, and then we will see comments as well. Okay. So the next way that we work this, we can basically put over here 1 plus x square minus x square by 1 plus x square whole square dx. This one worked. Of integral from 1 to infinity 1 by 1 plus x square minus x square by 1 plus x square whole square dx. Now you know that this is just tan inverse x, so tan inverse x from 1 to infinity, and this one is integral from 1 to infinity of x square x by 1 plus x square whole square dx. And this is in fact pi by 2 minus pi by 4, so that's just pi by 4 minus this integral. Now for this integral, from 2-3 tries, after making some tries, again you will realize that if we let y as x by 1 plus x square. Like it just boils down to the same expression at the end. That's why it will be helpful. So let's try to see how it goes in. dy equals to 1 plus x square times 1 minus x times 2x by 1 plus x square whole square. Let this be y I because we are going to need this again. I. Okay, and now this is dy equals to 1 by 1 plus x square minus 2 times x square by 1 plus x square whole square. So you see, uh, if if this integral that we have over here, this was to be integral z. Integral z doesn't sound good. Integral, let's say j. If this was integral j from 0 to infinity, x is x by 1 plus x square whole square dx. Yeah. First of all, so this is what the derivative dx. And now after this, after we have raised this form, it's probably better to do integration by parts. I think we will do integration by parts. Yeah, I think that's how I've done it over here. Okay, so basically we got this thing, and now okay. So this thing, the dy that we have over here, this thing that we have over here is just integral from 0 to infinity of how do I just write this? This thing is in the dy. Yeah. So we have dy equals to 1 by 1 plus x square minus 2 times y. That's how I think I can write dx. Okay, so that's what we have over here. And now it's been a little bit difficult, I think. Yeah, okay, now after we have that, let's just try. I think we will make it in some time. Yeah, and now after we have this, what else we can confirm? Dy equals to, okay, so what else can we confirm over here? So this is, if we let this as y, so this was y and we had 2y. Okay, now I have 1 plus x squared dx. Let me give some time for it. Okay, so first of all, let me try it again. Try another way. So we have pi by 4 minus integral from 0 to infinity. We have x square. Let me make it plus. So we have minus x square, and then but will that really be helpful? What did we have over here? We had minus x square plus 1 by 1 plus x square whole square. So this dy is actually this thing. So I think we can get to this expression anyhow. Let's just not see for let's just see this for some time. let's just do this for some time, and we can get to that. Minus x square plus 1 minus 1 by 1 plus x square dx. Yeah? And that's pi by 4 plus integral from 0 to infinity, and it's whole square actually. Now we know that this expression is just d of x by 1 plus x square. Yeah, this expression over here is just derivative of x by 1 plus x square, and then minus 1 by 1 plus x square whole square dx. Okay, so I think now we are finally done. Okay, so and this is I, and now after this we'll have I equals to pi by 4 plus x by 1 plus x square from 0 to infinity, and we know that this integral from 0 to infinity of 1 by 1 plus x square whole square, this was the original integral I. Yeah, this is just the original integral I. So we'll have I equals to pi by 4. At infinity, x square will dominate, so it's going to be 0. And minus at 0, this is going to be again 0, since it's 0 by 1. It's again 0. Minus I. Oh, wait. Is it from 0 to infinity? Oh, this is from 1 to infinity. There have been a lot of mistakes today. 1 to infinity. 1 to infinity. 1 to infinity. So at 1, this is just 1 by 2. Okay. I don't think if I didn't have guide, I would have been able to make this. So pi by 4 minus 1 by 2. So I equals to pi by 8 minus 1 by 4. I think that's the answer now. Yeah. And basically, we did not need this kind of manipulation. That's a really difficult one. Okay, and I think that was the only thing that was needed. And we could express it this way, and this was just d of x by 1 plus x square, and so the original integral. So let it I, and yeah, we could solve this. So this was a really good integral, and I think what's the response there in YouTube? I'm excited for that. Oh, okay, so there are a lot of people, and I really love to see them. Okay, so we are just doing some integrals. Let's go to the next one. Next one will be quite challenging, and I think it will be really nice to do it. And I'm really thankful for your support. Let's do next integral. From MIT Integration B, we are doing integrals. Okay, so our next integral is this one. Question number 16. So for question number 16, we can first try to factorize this expression. Integral from 0 to 1 dx by x to the power 4 minus 9x square minus 4x square plus 36. Yeah, an integral from 0 to 1 dx by, this will be x square minus 4 x square minus 9. Yeah, you can just see that we can take x square common, x square minus 9, and minus 4 common, x square minus 9. So we will have this. Now we can use partial fractions. So if we want to break this down into partial fractions, so first of all, we can just let x square as y for some time while we are doing partial fractions. So we will have 1 by y minus 4, y minus 9. Now if we want to break this, we will have one of the fraction with y minus 4 and other with y minus 9. Now we will use cover-up rule to find the coefficient that will have a numerator for y minus 4 and y minus 9. So cover-up rule says that, so if you want to find this term, first of all, we have to find what makes y minus 4 0. So if y equals to 4, we will have y minus 4 as 0. Yeah, and so just cover the y minus 4 and substitute y equals 4 for remaining expressions. The remaining expression is y 1 by y minus 9. So 1 by 4 minus 9 is what we will do. Now for this one, 9 makes it 0. So just cover 1 minus 9 and substitute 9 for other expressions. So 1 by 9 minus 4. So that's minus 1 by 5 by y minus 4 plus 1 by 5 by y minus 9. If we take 1 by 5 common, we will have 1 by y minus 9 minus 1 by y minus 4. So that's the partial fractions. Yeah, and note that covariable can be used only if there are first degree expressions. Since there are first degree expressions, we can use it. We cannot use it for other second degree expressions or so on. So now we know that the partial fractions for this is 1 by 5, 1 by x square minus 9 minus 1 by x square minus 4 dx. Now after this, I don't think it's tough. It's that tough. Now we can use the standard formulas. For this, we will have 1 by 3 ln of x minus 3 by x plus 3. Sorry, not 1 by 3, 1 by 2 times 3. 1 by 2a ln of x minus a by x plus a. And minus, this will be 1 by 2 times 2 ln of x minus 2 by x plus 2. And now we can go from 0 to 1. So we will have 1 by 5, and here we have 1 by 6 ln of now this per 8 1, this is just minus 2 by 4. Okay, and at 0 we will have minus 3 by 3. Yeah, but that will be subtracted, so we will just reverse that. So minus 3 by 3 goes into 3 by minus 3, and minus 1 by 4, again the same thing. At 1, this is just minus 1 by 3, and at 0, this is just minus 2 by 2, and we will reverse that, 2 by minus 2. Yeah. And then we have, again, I can just erase this for some time, just we can read it now. Now this will be 1 by 5, 1 by 6 ln of 1 by 2 minus 1 by 4 ln of 1 by 3. And yeah, I think that's the answer. And yeah, and we can just reciprocal this by changing the sign before the ln. That gives us 1 by 20 ln 3 minus 1 by 30 ln 2. And that's the answer. That's the answer. Let us check. Let us check the answer. 120 ln 3 minus 130 ln 2. Yeah, that's the answer. Let's check our response too. Okay, so I think the response is same. Now let's go to the next one. Oh yes, this is live. Someone is asking, is this live? Yes, this is live. Oh yeah, this is right. Okay, yeah, yes, I can read comment, and you can also suggest the solution for the problems that I'm doing right now. Yeah, let's go to next problem. This one. Can suggest how will we solve problem number 17? What substitution we shall make? Delete. Okay, so can you suggest what substitution we can make? Easy question. Okay. Yeah, it's probably it's an easy question though. We can just substitute ln x as y. So if substitute y as ln x, we have dy equals to 1 by x dx. So we have integral of ln y, and then 1 by dx by x is just dy. And now it's standard integral of ln x dx. We all know, and that's x ln x minus x. And we can also do it by integration by parts to get this result. So we have y ln y minus y plus c. And now y is just ln x. So we will have ln x ln x minus ln x plus c. So that's the answer. Yeah, that's the answer. Now let's go to next integral. Okay, so next integral is this. Delete. Now, so for this integral, we can basically change it to tan, and we will get a standard formula. Okay, let's see that. Let's do that. So this is tan x plus 1 by tan x minus 1. If we just do the reciprocal and take LCM, minus 1 dx. Now we can change it to tan a plus tan b by 1 minus tan a tan b. We can take minus common first, and then we can write it as tan a plus tan b by 1 minus tan a tan b dx. Now minus integral of this is just tan of pi by 4 plus x dx. So this will be minus of, now integral of tan x is basically just ln of sec x plus ln of sec x. So we have ln of sec pi by 4 plus x, and the coefficient of x is just 1, so we don't need to do anything else. And yeah, this is the answer. And we can just use this minus sign to reciprocal this to get ln of cos pi by 4 plus x. We can also expand this if you want, and we not dx over here, and then we will have ln of cos a cos b minus sin a sin b plus c. Now we can just take 1 by root 2 common, and then we can just make ln of 1 by root 2 plus ln of cos minus sin x. Yeah, and ln of 1 by root 2 is just constant, and it dissolves into constant. So that gives us ln of cos x minus sin x plus c dash. So that's the answer. Now let's go to the next one. Next one is question number 19. And if you have to check the answer though, yeah, it's the same thing though. Here it's sin x minus cos x. Cos we are also giving a modular sign over here, neither. So we will give a modular sign in ln. That's why it's same thing to write sin x minus cos x or cos x minus sin x. That doesn't really matter. Plus c dash. Yeah. Let's go to the next one. Now for this problem. Okay, so yeah, this problem. Okay, so for this problem, we have integral of cos x by x plus sin x by x times x plus cos x. Okay. What do you think we can do? If we just take minus x minus sin x. Okay, so we can basically dissolve this expression into the sum and derivative of this expression. So what we can do is we can have cos x plus x sin x, cos x plus x sin x as as something like the derivative of this expression plus this original expression as well. Yeah, and that way it will help, I guess. Okay, so what we can do is we can basically write this expression as x minus x times 1 minus sine x plus x plus cos x. Yeah. So, but how do I know this? By just hit and trial. I'm not hit and trial, but I try to see if I can write this expression as this original expression and its derivative. And so on the way to manipulating this just term with this expression and its derivative, I found a way to write it. Yeah, and it's by this way. So this is just minus x plus x sin x plus x plus cos x. Yeah. Yeah. Okay. So you can also do like this. You can just first of all you can introduce a x so that you can make same as the expression that's given below, and then again we can subtract that x. Yeah. You can also build your thought process like this, and then x by x plus cos x, and then dx. After this we will have x plus cos x, but also here if we take minus x common, 1 minus sine x will be a derivative of the denominator by x times x plus cos x dx. Now we will have 1 by x minus, we will have 1 minus sine x by x plus cos x dx. And so this will be ln x and minus ln of x plus cos x. So that's the solution, plus c. So that's the solution for this problem. And let's go to the next one now. Yeah. Next is this thing, sin x plus sec x. Sin x plus sec x. For this one, what do we basically do? We first dissolve sec x to cos, and then after dissolving this to cos, we can just change that, and just change that to cos sin x. Okay. Okay, so for this one, from 0 to pi by 2, we will have cos x dx by sin x cos x plus 1 dx. Yeah. The next thing, we will try to have 2 sin x cos x over here so that we can change this. So you can, it will be a standard form. So we can have 2 cos x dx by 2 sin x cos x plus 2. Okay. And now after this, like we are going to use techniques. So the technique is something like this. So basically, we will write this as, I will give you the reason why I'm doing that. Right? So we will write this as cos x plus sin x plus cos x minus sin x. Yeah, cos x minus sin x. And the reason for that is cos x minus sin x. And the reason for that is at one time we can make this as, we can write this as sin x plus 1 and plus 1. And 1 is just sin square x plus cos square x. Yeah. And if it's sin square x plus cos square x, so basically we can just break this into 2 fractions first of all. And over here the manipulation will be sin x plus cos x whole square plus 1, and over here that will be, we will just first of all take a minus sign over here, and then we will have minus 2 sin x cos x minus 1, and then again minus 1. Yeah, and so in that way we have to introduce a plus 1 and do it minus 3, and then we will have sin x minus cos x whole square, and then we had that minus 3. Yeah, but minus 3 when minus is taken out common, so we'll have plus 3 over here. Okay, I guess you understood this. We are just breaking this into two fractions. Since now we have this derivative of this expression in the numerator, and that makes it simpler now. I guess you understood what we have done over here, and it's just minus, this is 1 by root 3 tan inverse sin x minus cos x by root 3, and then plus this will be 1 tan inverse sin x plus cos x, and it will be from 0 to pi by 2. Okay, and at pi by 2 this will be sine of pi by 2 is 1 minus 0, so minus 1 by root 3 tan inverse 1 by root 3, that is pi by 6 plus, and this is 1 plus 0 again, so tan inverse 1 is just pi by 4, and then minus here sine 0 is 0, this is just 1, so minus 1 by root 3. That's minus pi by 6, so minus 1 by root 3 times minus pi by 6, and then plus this again pi by 4, so pi by 4 get cancelled out, and this thing and pi by 4 gets cancelled out, but this thing also gets cancelled out, is it? No, it gets added, I think, and that gives us minus pi by 3 root 3. Is that the answer? No, that isn't really the answer. I think I made a mistake over here. I think I did make a mistake over here. Okay. So when it's pi by 2, then yeah, this goes to 0, but for this one, okay, so for did I do wrong for this one? We take minus over here, sin x minus cos x whole square minus sin x minus 2. Okay, so this is actually minus 3. Yeah, plus 1 and minus, yeah, this is actually minus 3. Yeah. So that was a mistake, and I think I need to do it again. Let's do it again. Let us do this again. It happens. We just know from the mistakes. We learn from the mistakes. Okay, that's the law of the nature. So let us do it again. I think it's better if we just. Okay, so let's do. So we have minus, then 1 by 2a ln of x minus 3 by again there will be problem, I know, because before doing the integral I should have multiplied minus sign with the denominator, so that this will be plus and this will be minus. Okay, I cancel this out and this will be plus and this will be minus. Okay, now that will be fine. 1 by 2a ln of a plus x by a minus x minus x minus x minus sin x plus cos x. This goes from 0 to pi by 2 plus, and this will be tan inverse sin x plus cos x. That also goes from 0 to pi by 2. I think now we'll get the correct answer. So this is 1 by 2 root 3, and this is ln of root 3 plus 1 minus 0 by root 3 minus 1. So this is what we have at pi by 2, and then minus at 0 we will have, let's just divide, let's just why did that happen? 3 plus 1 with, and just divide at 0. This will have root 3 minus 1 by root 3 plus 1. Okay, and plus this will be just tan inverse 1 minus tan inverse 1. Yeah, so that's just 0. Why did I not notice it earlier? And then 1 by 2 root 3. We will have ln of, this will be just 4 plus 2 root 3 by 4 minus 2 root 3. And that will be 1 by 2 root 3 ln of 2 plus root 3 by 2 minus root 3. So I'll come with that. So 2 plus root 3 by 2 minus root 3. Now let us try to multiply numerator and denominator by 2 minus root 2 plus root 3. So we get 1 by 2 root 3, and we have ln of 2 plus root 3 whole square by 2 plus root 3 times 2 minus root 3 is 4 minus 3, that's 1. So we get 1 by root 3 ln of 2 plus root 3. So that's the answer. Let me check. Yeah, that's the answer. A video, some question came in my paper. Oh, with title. That's fine, that's fine. Okay, let's just do the next one. Let's do the next one. Now this problem. Okay, but before I do this problem, I just want to pause for a few minutes. I should really see an option over there. I will just block my camera for some time. I will return in just 1 minute, and I think I want you to wait for that. Yeah. So I'm back. I will just drink some water and we shall continue. No, I'm Nepali. Yeah, if even if you are Indian, there are chances to get admission in American universities. Basically, you have to apply through Common App, and you need to have good extracurriculars, good essays, and good honors, academics. And with that, there are a lot of people going to US from Nepal, India, and other countries too. So yeah, you have a pretty good chance if you have good academics and you are doing better in your extracurriculars. Oh, yeah, okay. So let me continue. Let's continue. Okay, so now we'll be doing this integral. Now for this integral, I think the good way would be to assume that y cos e to the power x at the beginning. Now we will have dy equals to e to the power x dx. So dy will be y dx, and then dy by y equals to dx. Now the integral will go from 1 to infinity, and dx will be just dy by y and root under 1 plus y square. Now after this, we can basically take y square out as common, and if we do that, y square out, we will have y to the power minus 2 plus y to the power minus 1 plus 1. Now the reason I did this is, now we can let z equals to 1 by y, and then we will have dz equals to minus 1 by y square dy. Yeah, so that's why minus dz equals to 1 by y square dy. So we have integral from 1 to 0, and then this will be minus dz by root under 1 plus z square. After this, we can just use the negative sign to just reverse the orders of integral to make it from 0 to 1 dz by root under z square plus z plus 1. Now it becomes a standard high school integral, and that's really easier. Integral from 0 to 1 dz by root under, now this can be written as z plus 1 by 2 whole square plus root 3 by 2 whole square. So that's why we can have, now the formula for this is, formula for the integral dx by root under x square plus a square is ln of x plus root x square plus a square. Now we'll use this, that gives us ln of and okay, and wait, yeah, okay, fine. Ln of z plus root under this will give us again z square plus z plus 1 from 0 to 1, and then this will be ln of 1 plus 1 by 2 plus, this is 1 plus 1 plus 1, that's root 3 minus ln of 1 by 2 and then plus 1 as well. Yeah, I think I'm doing good. I think it's going good. Yeah, okay, yeah, it's fine. And then it's ln of 2 plus 1 plus 2 root 3 by 2 multiplied by 2 by 3. If we merge these two, and then we can cancel these two out, and that's just ln of 1 plus now this is, I guess this is 3 plus 2 root 3. Yeah, that's 3 plus 2 root 3. Let me do it step by step. So ln of 3 plus 2 root 3 by 3, and that gives us ln of 1 plus 2 times 1 plus 2 times 3 to the power 1 by 2. Yeah, and that's the answer. But what you can do is, you can also do the other way. What you can do is, you can just divide numerator and denominator by root 3, so that gives us 2 plus root 3 by root 3. Yeah. And that gives us ln of 2 plus root 3 minus 1 by 2 ln 3. You can also write it like this, and I think that's what given here. No. Yeah, okay, so ln of 2 plus root 3 minus 1 by 2 ln 3. So I'm currently at Nepal. Yeah. If you are asking my location, substitute. Yeah. Now let's go to the next question. Question number 22. So this one is probably most common question that can be seen everywhere. This is a kind of common question that's asked in many places. First, what you need to do is just substitute y as x square, and then we will have dy equals to 2x dx. Yeah, and then dy by 2 equals to x dx. Again, do that, and then this will be integral from 0 to 1 y e to the power y dy should be dx. Yeah, now x dx is just dy by 2, so we will have 1 by 2, and now if we integrate this, y e to the power y minus e to the power y, we can do this by integration by parts from 0 to 1, and at 1 this is 1 by 2 e minus e, at 0 this is 0 minus 1, so that's 1 by 2. Yeah, let's go to next integral. This one is quite good. Did it. Okay. So now for this one, we just first of all we need to find out what this expression values to. So we just let this as y, 1 plus x, and under 1 plus x, and so on. Okay, and then we will have y equals to under 1 plus x times, this will be just y itself, since that was what we assumed earlier. So this is y square equals to 1 plus xy, and y square minus xy minus 1 equals to 0. Now you can use quadratic equation, and that gives us y equals to minus b plus minus root b square minus 4ac by 2a. Yeah. Now, and since this is a positive expression, yeah, we have plus of the square root, so we shall have a positive answer. That's why we just take the positive sign, x plus root under x square plus 4 by 2. This is into yeah, this is 4. Okay, so this is x plus root under x square plus 4 by 2. Now you can solve it. X plus root under x square plus 4 by 2 dx. Now if we integrate this, we will have x square by 2 plus, for this one we will have x by 2 root under x square plus 4 plus a square. A is 2 over here, so a square by 2 ln of x plus root x square plus 4. This is the standard formula that you need to know from 0 to 1. Now 1 by 2. At 1 this is 1 by 2, at 0 this is 0. Okay, and for this one at 1 this is root 5 by 2, at 0 this is 0 plus, and now at 1 this is 1 plus root 5, at 0 this is just 2. Yeah, and now next, now this will be 1 plus root 5 by 4 plus ln of 1 plus root 5 by 2, and that's the answer. Okay, let's check. One plus root 5 by 4 plus ln of 1 plus root 2, that's the answer. Okay. Sai has left. Good job, bro. Then see, pick up, code doing the hard one. Okay, let's go to the next one. Let's go to the next one. Yeah, now this one. This is also a kind of popular integral since it has a specific way to be solved. I'll just drink water. Okay, so let's continue. So this can be solved basically by using integration by parts, where you take 1 by log x as u and 1 as v. So we'll have 1 by log x, and the integral of 1 is just x minus, and now the derivative of this thing is just minus log x to the power minus 2 dot 1 by x. Now the integral of 1 is just x dx. Yeah, and after this we just integrated this expression of on the first. Second will be as usual, nothing changed. Now this is x by log x, and this is just plus 1 by log x square. Yeah, the x will cancel out, and this is just minus 1 by log x square dx, and these two will cancel out, so that's just x by log x. You see, so x by log x is the answer. You can check it online. Yeah, and now we have the final integral from 2010, and we still have a lot more to go. Okay. But let's just keep patience and solve these integrals, and just hope that one day all of them will be solved. Okay, and for this one we just have a direct formula from beta gamma functions. Yeah. So we have a formula that integral from a to b of x minus a to the power m minus 1, b minus x to the power n minus 1 dx, This is actually equals to b minus a to the power m plus n minus 1, and then beta of m and n. We'll just use this formula directly. We'll not take any more. So 2 minus 1 to the power random power. I will find it out because 1 to the power anything is just 1. And then beta of m is just it is a m minus 1. So m minus 1 is 1 by 2, m is 3 by 2. 3 by 2. And n is also 3 by 2. So this is just 1, and then this is gamma 3 by 2, gamma 3 by 2 by gamma 6 by 2, that's just gamma 3. So this is 1 by 2 into gamma 1 by 2 is root pi. Again 1 by 2 into gamma 1 by 2 is root pi. And gamma 3 is 2 factorial, that's 2. So we have pi by 8 as the answer. And with this we have completed the first one of 2010. Now let's go to 2011. Okay, and let's just delete a new page. And just the time, how much has been time. There are 7 likes already, and that's a good thing. And concurrent viewers are 0, and the duration of the video has been around, it's already 2 hours. With this speed I'm going to take 20 hours. That's almost an entire day. Okay, I'll just try how much I will be able to. Okay, so now it's time for 2011. Okay, so this problem. So for this one, I think it would be better to do it in a different video, I guess. Yeah. So I think I will end this live over here, and I will do a next. I think that will be fine, cause this can get messier if it's long. Yeah. So I think, yeah, let us see in the next video where we solve problem from MIT Integration B 2011. This is all for now.